Okay, good morning, everybody. Can you hear me well? Now, let's start with some housekeeping items. First, I already have my CASA tutoring hours. So my office hours are in CASA, the online tutoring center there. It would be on Tuesdays and Thursdays from 6 to 7 p.m. But if you are not available during those times and you have some urgent questions, then either you can send me an email or you can still drop by the CASA Tutoring Center. I posted in our lab meeting channel the schedule for the CASA Tutoring Center. So those are the times where there are TAs that they are hold on, let me just fix that. There's an echo, probably because of my tablet. Okay, I hope this is better now. Okay, so yeah, those are the times where there are available TAs in CASA for 1432. So yeah, take advantage of CASA. And then what else? I already uploaded the annotated version of the file of the worksheet that we started working on last time, together with the video recording of last labs meeting. So you can check out my website or via the posts in MS Teams. So you will see this in our MS Teams lab meeting channel. So I'll post the links there. But if you want to go to see them in a complete list, go to the top of the tab. You will see Neil's website there, and then click on that. You will be diverted to my webpage for this class, so that you will have a complete list of the things that we already have. So in case you missed the lab meeting, just go over there and watch the video recordings and then look at the worksheets. Again, I always have two versions of the worksheet. One is the blank one, which you can write on and then answer it on your own. You can do it beforehand or after the classes as a review. And second are the annotated versions, which includes everything that we did in class, so the solutions I made for those particular problems. So you can go over that, check your solutions if you tried answering them beforehand, or you can read those and then see if you understand those things. I usually include all of the details in my solutions. That helps me a lot in keeping track of the solution. And also it will be it is beneficial also for you so that you can read line by line what steps I took in the problem. But in exams, again, you don't need to write all of those tiny details if some steps are insignificant, or you can do the calculations in your head, then that's fine. You can skip those, but keep the necessary and essential parts of the solution in your work. All right. What else? Oh, by the way, I uploaded also a formula cheat, sort of formula cheat sheet, which will help you recall those formulas that you were supposed to remember from Cal 1, plus some extra that we will encounter later. Let me just start sharing my screen and show you what I uploaded. Okay, so I hope you see my screen now. So this is the file that I uploaded in my website. Actually, this is just something I downloaded from the net, which compiles some of the basic formulas that we will need. So you have those basic derivative rules here, properties of integrals, then some integration rules. I just annotated there a little bit. And then, yeah, these are just the basic formulas you need to recall. Of course, there are some more. But I guess these are the most basic ones that at least you should memorize. And then there's some bunch of pages, 2 to 4, include some things that we will see later in the class. So this is also a good preview of what we will be doing. I uploaded this in my website. So again, go to the lab meetings channel. On top of that, you will see a tab named Neil's website. Go over there and you will be directed to my webpage, and it is somewhere at the end. So you look at other materials, you'll see the integral formulas cheat sheet. All right. Of course, you can find some other version of it. It's a pretty generic cheat sheet. You just go on Google and search for integral formulas, then you'll see some. But this is, I guess, the most simple that I found. So yeah. Okay. And then let's go to the worksheet. Worksheet 1, lab 4. Okay. Okay, here you go. And then I remember I mentioned to you to try to answer problems 5 to 19. Problems 5 to 19 are questions pertaining to the elementary properties of integrals, like the fundamental theorem and integration, basic integration rules. And then those from section 6.3 will just require direct application of those basic rules plus the basic integration formulas like the power rule, and then using the table of integrals like how to integrate the basic functions or elementary functions, which are the ones that we have encountered from derivatives, right? Because again, derivatives are just differentiation is just a reverse process of integration. So if you know a function is the derivative of another function, then that means that's the integral of such a function. All right. So did you guys find some time to answer problems 5 to 19, or at least go over and look at them? Any problems with these? By the way, if you already tried some of the online quizzes, some of the homework problems, and you have some questions about them, just feel free to send screenshots of your questions in the chat. I'll be happy to help you with those problems. Also, if you are trying some problems somewhere, say from the textbook or from another book that which is related to what we are discussing today, just send them in the chat. To answer Katie's question, there is no complete answer sheet for this worksheet, but what I'll do is whatever I write here in this worksheet will be available to you. There's a lot of questions here. I don't think we will finish answering everything, or probably we'll just answer some of them, but I'll upload this material that will be the result of our meeting today. But if you find some interesting problems that we didn't discuss, let me know the problem number and I will include them in my solution. All right. But in succeeding worksheets, I'll try to, as much as possible, write the answers. Okay, that's a good idea. Probably, Katia, I can write the answers for problems 5 to 19. I'll just write the answers and then I'll leave the work to you so that you can write your answers. But as promised, for problems from section 6.4, I'll go over some of this in details. Fatuma is suggesting we go over problem number 10. Let's see. Oh, sure, no problem. Maybe we'll start here. Any other suggestion from this worksheet? Because I want to focus more today on section 6.4, which is basically integration using u-substitution. Okay, but no problem, Fatuma. I can walk you through problem number 10, and this would be a good springboard before we go to the problems from section 6.4. Okay, so here let's try solutions to some problems. So let's start with problem 10. Oops. Okay, so for this particular problem, I see that maybe the cost of the difficulty here is that we have a denominator x. But the thing about this is a quotient, and we expect that integrating this will require some more work because differentiating a quotient requires a quotient rule, which is a complicated formula. So as integrals being the reverse process of integration, we expect a complication whenever integrating a quotient. But unfortunately, we don't have a straightforward quotient rule for integrals. So we try some techniques in order to eliminate the quotient. So there are usually two ways how to deal with this. Number one is to simplify the quotient. I mean, performing the division. And I guess that will apply for problem number 10. And the second way is by using u-substitution, which we shall address with problems from section 6.4. So having said that, here, the trick is to carry out the division. So you are dividing by x. And this is the good thing about dividing by a monomial. If you are dividing by a monomial, a single term in the denominator, you can simply divide each of the terms in your quotient, in your fraction, and that's it. That will give you the quotient. So in this particular problem, if I carry out the division by x first, I'll have this 2x squared all over x. That will just be 2x, right? And then next I'll have 4x over x. That will just be plus 4 dx. Good. And now I have a simple sum, which can easily be integrated. So the integral of 2x is 2x squared all over 2. Then integral of 4 is 4x. But this is a definite integral, so I would need to evaluate everything from 1 to 2, right? But I can simplify first. This would be x squared plus 4x, evaluated from 1 to 2. And then the fundamental theorem of calculus will kick in. We plug in the upper bound minus plug in the lower bound. So I'll plug in the upper bound 2, so I'll have 2 squared plus 4 times 2 minus, I plug in the lower bound, so I'll have 1 squared plus 4. And then simplify this, I'll have 2 squared, that's 4 plus 8, so that's going to be 12 minus 5 equals 7. Okay. Did you guys get the same answer? For those who tried it already? I hope I didn't mess this up. I hate doing arithmetic, so kindly double check my arithmetic. But I hope that's fine. All right. I hope, Fatuma, that helped. Okay. So if there are no other questions for problems 5 to 19, let's go to problems from section 6.4. And as I've mentioned, these problems involve u-substitution, right? So let me begin with some easy ones. And then as we go along, let's answer some of the more complicated ones. Again, if you encountered some complicated problems that you want to discuss today, just let me know in the chat and I'll be happy to work those with you. But while waiting for that, let me go to some of my choices. I'll start with the easier ones, then go ahead with the more difficult ones later in the class. So I'll begin with problem 22. So this would be the integral of x squared, square root of x cubed plus 1 dx. All right. So what's going on with this integral? Well, in this integral, you notice that the integrand involves a product. It's x squared times the square root of x cubed plus 1. And since we are integrating a product, we expect some complications here because differentiating a product involves the product rule, right? But unfortunately, we don't have an explicit product rule for integrals. So that means here I need to get rid of the product first. And how do we get rid of the product? Well, the usual technique is to use u-substitution, right? So when we say u-substitution, you will pick one function to be renamed to a monomial u, and that is designed so that the integration will be in the form of an elementary function. And when I say elementary function, this is one of the functions that we see in our table of derivatives. And then the only thing here is that your choice for u should give you or should require a readily available du. Because the thing here is, in the next step of my solution, I want to write everything in terms of the variable u. But the deal here is when you change one variable to u, you change everything to the variable u. So in the next integral that I will write here, everything should be in terms of the variable u. And that includes the differential. So I have a dx to begin with. If I change the integrand into the variable u, then I should have a differential du, right? And basically that's the goal. And that's the hardest part. you should be able to get an appropriate du so that whatever is required to get the du is already present in your integral. So here, usually, whenever dealing with products, your choice or the good candidate for you would be something coming from the more complicated ones, from the more complicated factor. In this case, I guess the more complicated one is the square root of x cubed plus 1. But if I will let u to be equal to the square root of x cubed plus 1, the derivative will involve what? The derivative will involve x cubed plus 1 raised to the negative 1/2. And you see, I don't have some square root in the denominator. So I guess letting u to be equal to the entire square root would be complicated, or that will require a complicated du. So that means, no, I won't let u to be equal to the square root of x cubed plus 1. And I'll go to the next best thing. Let u to be equal to simply x cubed plus 1. And hope that I get a nice du. And this substitution will make the integral much simpler than the original form, right? So let's check if indeed u equals x cubed plus 1 is a nice substitution. Well, how do we do so? Look for du. Take the derivative of both sides. So here we get du equal to 3x squared dx. And check if this is readily available in the integrand. So I already have an x squared here. I already have a dx here. What I'm missing is a factor 3, right? But missing constant factors can easily be dealt with because here I can divide both sides by 3. So I'll have du over 3 equals x squared dx. This means x squared dx can be replaced by du over 3. So if I go back to my integral, the highlighted factors x squared dx will be replaced by du over 3, right? And the unhighlighted portion should be expressed entirely in terms of u, right? So the square root remains, but x cubed plus 1 will now be simply u. And you see here that, oh, this is a much simpler form than the original one. In fact, this is an elementary form. We can rewrite the integral by taking out the 1/3, the constant factor, out of the integral, and then expressing root of u as u to the 1/2 du. And here you see I can simply apply here the power rule, right? So applying the power rule will give us 1/3 u to the 3/2 all over 3/2 plus the arbitrary constant c. Don't forget that arbitrary constant c. And then I'll carry out some of the arithmetic here. I'll get 2/9 of u to the 3/2 plus the arbitrary constant c. And then the last step is to revert to the original variable. The original problem is in terms of the variable x, so I'll just revert the u's into x cubed plus 1. So doing that will give me 2/9 times x cubed plus 1 raised to the 3/2 plus the constant c. And that's my final answer. All good? Any question with this? Any reaction, guys? Okay, great. Let me try another one. It doesn't matter how complicated the integral is, whatever functions are involved, the same principle applies. Just pick a right u. How do you know that's the right choice for you? Take du and see if it's readily available in your integral. So let me try another one. Let me pick something. Okay. Let me try this. This is number 36 from the worksheet. Integral of x squared e to the x cubed plus 1 dx. Okay. Again, this is a product, though more complicated than the previous one because this involves the exponential function. But let me try the same scheme nevertheless. I'll take a look at what could be a nice choice for you. Well, what would be the choice for you? I said most of the times it always comes with the more complicated part of the equation of the integrand. In this case, it's e to the x cubed plus 1. But if you let u to be e to the x cubed plus 1, right? So du will be what? Du will be e to the x cubed plus 1 times or actually it did work. I was thinking this won't work, though it will work, but it is a little bit complicated because you see that this would be e to the x cubed plus 1 times 3x squared. That's a long expression there, though it works because yeah, I am now regretting that I tried doing this first because it did work. I thought this won't work. But anyway, yeah, this will work, though I guess this is not the simplest substitution, right? But if you would like to use that, go ahead. What I'm trying to use here is a more simpler substitution, which is just letting u to be the exponent of e. So I can let u be equal to x cubed plus 1 because you want to keep the du as simple as possible. The previous choice I did, the previous choice of function I used will work, though it gives me a complicated du. And there's nothing wrong with using that complicated du. I just want to keep my solution simple. So in this particular case, letting u be equal to x cubed plus 1 would be a lot simpler, but will give me the same answer as what I would have gotten if I used the long one earlier. So du will be what? 3x squared dx. And let's see if we have that present in the integral. I already have the x squared there. I have the dx there. What I'm just missing is the factor 3. But as we have seen in the previous example, a missing factor is not a big deal. You can just divide both sides by 3 to see that x squared dx can be replaced by du over 3, right? So that means this integral, the highlighted factors will be replaced by du over 3. We'll be left with e to the x cubed plus 1. And my goal is to write that in terms entirely of the function u, of the variable u. But that's easy. It will just be e to the u, right? And then this is 1/3 integral of e to the u du, an elementary form, which is easy. This will just be 1/3. Integral of e to the u is simply itself, plus the arbitrary constant c. Final step is to revert to the original variable. Okay, so I hope this example brings back memories of Cal 1 so that you will be prepared, because in the coming weeks we will be working with more complicated integration rules. So yeah, take note of this ones. Let's see, next problem. Okay. If there are no reactions from the chat, then I'll go ahead with the next problem. It's problem 23. Well, or I'll modify problem 23. Problem 23, the worksheet asks for the definite integral from 0 to 1. But I don't want to do the arithmetic. I leave that, guys, to you. So I'll just compute the definite integral. So it's 2x plus 2 all over the square root of x squared plus 2x plus 1 dx. All right. So this integral now is a quotient. And we expect a complication here because taking the derivative of a quotient is complicated. You need to use the product rule. So in turn, there should also be some sort of a complication for integration. But unfortunately, we don't have a product rule for integrals. So what we need to do here is to eliminate the quotient and write it in elementary form. And how do we eliminate the quotient, or sorry, eliminate the division here, is by redefining one of the functions and calling it by a simpler name, u. So that's why u-substitution will be helpful here. Now, there's no hard and fast rule on how to determine what should be the u. I always say it's just about a matter of instincts. Once you answer many integration problems, then you will develop a keen eye in determining what would be the nice choice for you. But if you're just beginning to do u substitution, probably trial and error would be a good idea to do. There's just a finite number of options for the function u. The only requirement is that you get a nice du, and when I say nice, that du should be right away present in the given integral, right? So having said that, well, for quotients, most of the times I try getting the u from the denominator. And what's the logic behind that? Well, if I will let u to be something from the denominator, I am reserving the numerator to be the source for my du. That's why the denominator would be my go-to first choice for the function u, right? And I'm hoping that the requirement for the du will be coming from the numerator. That works most of the times, but not all of the time. So we'll see some examples wherein the choice for u doesn't come from the denominator. But I suggest you try looking at the denominator first, and probably that would be sufficient. In this problem, the denominator is a square root. But again, the derivative of a square root is complicated, so I won't include a square root in my choice for u. I'll do so if extremely necessary, but if I can find a substitution that doesn't involve the square root, then that's fine. I'll start with that. Working with a square root is my last option. That's my last resort. So probably let's write the radicand, just the radicand from the denominator. So I let u be equal to x squared plus 2x plus 1, all right? And if that is the case, then du will just be 2x plus 2 dx. And I guess here you will see exactly why I started with the denominator. Because again, I'm hoping that the du, or the requirement for the du, will be coming from the numerator. And true enough, I need a 2x dx, and that's present in there. So that highlighted factors in the integrand will just be replaced by the du. So in my next step, I will have the integral of simply du all over the remaining ones. But the remaining ones is fine because it will just be the square root of just u. Okay? And if I rewrite it as the integral of u to the negative 1/2 du, I'll right away recognize that this is a very elementary form. This will just require the power rule to be evaluated. And true enough, this will just be what? U to the 1/2 all over 1/2. And don't forget the arbitrary constant plus c. And doing the arithmetic, this is c2 u to the 1/2 plus c. And final step would be to revert to the original variable. So this would be 2 square root of x squared plus 2x plus 1 plus the arbitrary constant c. All right. Any questions, guys? Do you follow? Are you still there? Or are you watching Netflix on another screen?
This is
Okay.
making sense. Thank you.
All right. Mm-hmm. Are these problems too easy for you guys? Okay, yeah. If you want to answer some more complicated ones, then just let me know what you think are the more interesting ones. But usually I start my discussion like that. I usually start with the easy ones just to keep things going. Because the thing here is that I want you to understand the process first before we go to the more challenging ones. And I guess we can start with the challenging ones. Somebody's asking problem 29. Sure, let's try problem 29. So for problem 29, we have the square root, the integral of 2e to the 2x times cosine of e to the x dx. Aha, interesting one. And sorry, there is no 2 here. Yeah, so it's just 2e to the x cosine e to the x. Okay. Now, this is a product, so we need to eliminate the product. Now, how do we get rid of the product in the integrand? We use u-substitution. Well, the u-substitution will come from the more complicated function. And what's the more complicated function here? Well, the thing here is Yeah, the complicated function is the cosine function. Okay, but if we let u to be equal to the cosine function, right? If we let u to be equal to cosine x, what would be the du? I hope you can imagine the next few steps before we write so that we can eliminate whether it's a right or wrong choice for you. If Leslie is correct, if we let u to be equal to cosine e to the x, then our du will involve sine x. In particular, it would be negative e to the x sine x. But nowhere in the integrand can you see a negative sine x. So that's a red flag for us. We cannot let u to be equal to cosine e to the x. So we go to the next good thing. If the entire cosine is not a good choice for you, then probably we go inside the cosine and look at what's the function inside the cosine. Inside the cosine, we see e to the x. And let's see if that will work. So if I will let u to be equal to e to the x, then what would be du? Du will be e to the x dx. And let's see if we have that in the integrand. Well, here I have the e to the x there. I got the dx there, so I'm good. I have the du. And I'm just hoping that everything will just be would be beautifully transformed into an integral involving only the function u, right? So the highlighted factors would be replaced by u. I have a 2 remaining there and a cosine e to the x, but we agreed to call e to the x simply as u. So this will just be cosine of u, right? This would be 2 integral of cosine u du, right? Which is an elementary form. We know what's the integral of cosine u, and that's what? That is sine of u plus the arbitrary constant c, and then we revert to the original variable. So this will just be 2 sine of e to the x plus the arbitrary constant c. Good? Okay. Let me see problems 28 and 30. Yeah, problem 28 will be the same, would be the same process. If you look at problem 28, you can let u to be equal to x squared. And then problem 30, you just let u to be equal to 5x. Yeah, same process. Yeah, Marion, yeah, I can walk you through questions on the quizzes and homeworks, but I need you to send me the screenshot of those problems so I can answer them for you. If these are problem from the online quizzes and online homeworks, I can walk you through them, even solve them, because if you take the quiz another time, then the questions or the numbers will be modified a bit. Uh, Insofar as homeworks are concerned, I can walk you through them, but I won't answer the entire thing. So I will leave some details to you, but I will leave some hints for that. Uh-huh. Yeah. Okay, I see your suggestion here.
Excuse me.
Well, sure. Yeah, go ahead.
I have a really quick question about this number 29.
Sure, go ahead.
Could you use the ex in the parentheses of cosine, or is that like not possible?
That's not possible because e to the x is inside a cosine function. So it cannot go out the cosine unless you apply some trig identities. But that remains inside. That's why you see here I still have cosine u, and u was still e to the x just in disguise. So I relied on the e to the x coming from the outside of the cosine, and that's what I used in order to get the du.
Okay, thank you.
All right. Okay. I see Marion posted a question here, though it's a little bit off topic, but yeah, let me just insert it right here. Let me call this example. I said I'll label problems that are not part of the worksheet. I'll label them with letters. So we already have examples A and B. So let's call this example C. So here, given f of x equals 1 plus ln of cosine x, find the integral of square root of 1 plus f prime of x quantity squared dx. Okay. Okay, this is in the homework, and the homework is not electronically generated. So that means if I answer this, then you all know how to, what's the correct answer. Well, probably I let this one pass. I'll answer it completely, but just don't tell Dr. Almas. I don't want to get into trouble, but anyway, yeah. This is our this is our first week, so yeah, I'll give this to you as a bonus. All right. But I hope, well, that's one thing about me. I don't hesitate answering some homework problems or any quiz problems, but I trust that you guys will not just copy the solution, but you will try to understand every part of it so that if you encounter a similar one in the exam or in other quizzes, you'll be able to answer them. All right. Okay, so at first glance, this problem seems to be very complicated because you want to get the integral of a complicated integrand, the square root of 1 plus f prime quantity squared dx. But if you will break this down into several pieces and do it step by step, it won't seem to be hard at all, right? Just a trivia or a spoiler. This is a important quantity. Probably that's why it is given here in this at this point. You will learn later that this is actually the formula on how to find the length of a particular curve. You will learn that later as we go along the course. But let's try to answer this. First thing, the integral involves f prime, but we are given f. So why not at first find f prime? Oops. Okay. F prime of x then would be the derivative of f. I hope you still remember the derivative of ln. So this would be 1 over cosine x times the derivative of cosine. I need to apply the chain rule here. So it would be negative sine x. Then this would be negative sine x over cosine x, which is familiar. This is negative tangent x. And I guess it would be hard if you won't write it as negative tangent x. So using trig identities and knowing them would be a big help here. So now I can start solving this integral because I know what f prime of x is. So, okay, let me go on the next page. Okay, oops. All right, so now I can plug in that value for f prime that we found. So this is integral of 1 plus f prime is nothing but negative tangent of x quantity squared dx. And then here I can simplify. This would be 1 plus tangent squared x dx. And at this point, this might look very difficult, but again, if you go back to your trig identities, do you remember what 1 plus tangent squared x is equal to? Or what's a simpler form for that? Yeah, that's correct, Kevin. 1 plus tangent squared x is secant squared x. And yeah, you're right. The crucial first step here is to find f prime because you want to integrate something that involves f prime. You're given f, so you need to find f prime. And finding f prime requires you to remember what the formula for the derivative of ln is, right? And then I simplify. I have a square inside the square root, so this will just be integral of secant x dx. And do you still remember what's the integral of secant x? Unfortunately, I don't think this is in the integral for in the cheat sheet that I uploaded. But if you go back to your notes in 1431, you will see that this is the ln of the absolute value of secant x plus tangent x plus c. Kevin, check that. I guess you are referring there to the derivative of secant. The derivative of secant is secant x tangent x, but what we're looking for is the integral of secant x. So be careful. Yep. Okay, sure. There you go. Yeah, don't worry. I will be uploading this entire worksheet at the end of the class. So, so you don't have to copy this. But I understand some students find it easier to learn if they are writing at the same time. So yeah. So just let me know if you want me to scroll up or down. Okay. But again, everything will be uploaded. Okay, so let's see. There's another problem in the chat. Yeah, this is a good one. Emilia sent a nice question, problem 16. I guess this is from the homework. It's a bit more complicated. I'll go back to it probably in the last 5 minutes of the class because it's more difficult than the other ones. Let me just pick some important problems here. Let's see. Okay, let's try problem 53. Problem 53, integral of ln of x to the fourth all over x dx. This is one of those times wherein choosing the substitution from the denominator will not lead you to the easiest solution to a certain problem. Because here, if you will stick to what I suggested earlier, it will let u to be equal to x, then du will just be equal to dx. There seems to be no point of doing this because you will have what? After doing this substitution, you will have ln of u to the fourth all over u du, which is exactly the same thing that you started with, except that all the variables x were replaced by the new variable u. So choosing the one from the denominator as your u won't lead you to anything productive, right? So this is one of those rare occasions. So we don't have a choice. So I'll try the numerator. Can I let u to be equal to x to the fourth? Well, if I let u to be equal to ln of x to the fourth, will I get a nice du? So let's try that. Okay. If u is ln x to the fourth, then the required du will be what? I differentiate ln. I'll have 1 over x to the fourth. Then chain rule kicks in. Derivative of x to the fourth is 4x cubed dx. All right. And then if I simplify, this will be 4 over x dx. And do I see that in the integral? Well, I have the dx there. I have an x in the denominator. And the only missing thing is the 4, right? But that won't be a problem. I can divide both sides by 4. So I'll have du over 4 equals dx over x. So that tells me that dx over x can be replaced by du. And ln x to the fourth is simply u, which is a lot more simpler than the original function, right? The original given integrand, right? So it's just the integral of u du. And if we integrate this, this will just be u squared all over 2 plus the arbitrary constant c, right? And then we revert to the original variable. I'll have 1/2. U is simply ln of x to the fourth raised to the second power plus the arbitrary c. And that's it. Okay, so just to illustrate that sometimes choosing the u from the denominator won't work. Okay. And then let me go to the question sent in the chat by Emilia. Let me see. So this would be problem D. Okay, if you guys want, you can take a screenshot of this. I'll give you 5 seconds before I go up. All right. let's do problem C. Was that C or D? This should be D, problem D. Okay, so Emilia sent this problem. I'm guessing again from the homework, 6x over root of 100 minus x to the fourth dx. Well, the u-substitution here will mean, I know that this would be coming from the denominator, right? But it won't be as straightforward as as we have seen in the previous examples. Oh yeah, thank you, Kevin. I forgot that. Yeah, thank you. I forgot that dx over x is du over 4. Good catch. Thank you. So that means this will have a 1/4 over here and a 1/4 over here. So this would be 1/8. Thank you. I forgot about that. Yeah. Dx over x must be replaced by du over 4. So the entire integral would be multiplied by 1 over 4. Good catch. Thank you. Okay. Now going back to problem D. U equals what? If I will let u to be equal to 100 minus x to the fourth, du then would be negative 4x cubed dx, something that I cannot get in the numerator, right? Because I only have an x, but it requires me to have an x cubed to get the du. So this is not an appropriate substitution. Taking u to be equal to the entire square root won't be productive either. So the thing here to do is to look at how the integral looks like and compare it with the elementary forms that we have seen earlier. Well, this is particularly the case when working with square roots in the denominator. You should always keep in mind the formulas for integrals yielding inverse trig functions, because they are the ones that involves square roots in the denominator. So what I'm saying is, okay, just remember this problem. If we go here in the cheat sheet that we have, look at this last column here. Yeah, they involve, these are the these are the integrals that yield inverse trig functions, right? And if you look at the second one, in particular this one, right? You see here that this is almost what we have. So in the denominator, we have what? Remember the problem we had is the square root of 100 minus x to the fourth. 100 could well be my a squared. But the problem here is I have x to the fourth. But here I should have something squared. So probably that would be the source of my substitution. And true enough, if I go back here in our problem, okay, I can let u to be equal to x squared. And you will see later why I decided to let u to be equal to x squared, right? Let's see if this will work. This will work if we have the right du. Well, du would be equal to 2x dx. And do we have this in our integral? Well, I have x dx already, but there's an extra factor 6 there. So what I can do is to multiply both sides by 3 so that I know exactly what to replace 6x dx with, right? So that tells us that 6x dx will be replaced by 3 du all over 100 minus x to the fourth. We said, okay, I'm going to let u to be equal to x squared. This means u squared is equal to x to the fourth. Agree? So that means that x to the fourth in the denominator can be replaced by u squared. Okay? And this can be rewritten again as 3 integral of du over square root of 10 squared minus u squared. And if you go to the cheat sheet that we have, or the formula sheet that you developed from Cal 1, you see that this is equal to 3 arcsine of u over 10 plus the arbitrary constant c. Good? And so the last step is to revert to the original variable. So here we have 3 arcsine of u, which is x squared over 10 plus the arbitrary constant c. Okay, guys, any questions with that? Let me just check one thing. Okay, any questions? Okay, sure, yeah. So this might be a little bit a non-obvious choice for you, okay? So why did I let u to be equal to x squared? Well, the thinking process goes this way. I started probably, if you're just starting to learn calculus, well, the first thing to do here, as I suggested, is look at the denominator. You let u to be equal to 100 minus x to the fourth. But as you have seen earlier, the du will then will be what? Negative 4x cubed dx, which is not present in the numerator. So getting that as your u is not a good choice because you will not get the needed du, right? Now, if that is the case, then the next thing that you can do is to compare this integral with the integrals yielding inverse trig functions, because the integrals yielding inverse trig functions are the ones that most likely um, uh, give us the right substitution here. So let me just copy this. Okay, and I'll go to my formula sheet here. So it's important that you still at least remember the gist of these formulas. Yeah, okay. So here we go. So this is a given expression that we have. And I recognize that, oh, this involves the square root of something in the denominator. So if I go back to my notes and look at the formulas involving such an integral, I'll see this one. Okay, and I'm going to compare the form that I have, but strictly just the denominator. I have a 100 minus x to the fourth. Well, a squared correspond to 100, so that means a is equal to 10. No big problem about that, right? So a equals 10. But the next thing here is that u squared. So I have a minus sign. That's perfectly fine. That corresponds with that. But the formula for arcsine requires a u squared. But what do we have here? I have an x to the fourth. So that means I need to find a way on how to rewrite the denominator to involve only a u squared, not an x to the fourth. So how do I get a u squared being equal to x to the fourth, right? Because I want to have a minus u squared in the bottom, but I was given an x to the fourth. But from here, you see that, okay, what I can do is to just take u to be equal to x squared. Okay. So that after the substitution, this x to the fourth will just be replaced by u squared, right? Because u squared equals x to the fourth. And then now here we have seen, okay, how do we get a nice form? But the next question is this an appropriate choice for u? Well, can we get a du? Well, du will then be equal to 2x dx. Is this present in our integral? Fortunately, yes. You have an x here, you have a dx here, and note that the x dx can be replaced by du over 2, right? So that's why we get the 3 in the numerator. Yeah, so it's just a matter of matching this integral with the known formulas that we have. But this is a little bit unnatural because you need to remember the formulas for the integrals that yields inverse trig functions. But as you get along, you will you'll realize that sometimes this is the key. So again, try the denominator or try something from the denominator as your u. But if that doesn't work, then if your denominator involves a square root, compare it with the formulas for integrals yielding inverse trig functions. Okay. So yeah, are there any other clarificatory questions? So I guess you guys are a little bit more shy than my previous class insofar as sending questions. So I hope next time you'll bring your questions up, or more questions coming from the quizzes, coming from the homework. I'll see if I can walk you through the entire solutions. If not, I'll give you some hints to go along the way. But yeah, let's keep this class as interactive as possible. So in an hour or so, I'll make all these materials available. So this version of the worksheet will be uploaded. Uh, it will replace the annotated version that we had from last time. So check out the website again. And yeah, that's correct, Faiza. If you want to discuss something from the homework or the quizzes, especially for the homework, because the quizzes, the numbers or the problems in the quizzes changes as you take the quiz again. But for homework problems, yeah, it will be great if you can send them to me ahead of time so that I can modify the problem a bit so that I won't be answering your homework problem. So yeah, that's the only reason why I want you to send it to me ahead of time so that I can modify it a bit. Okay, so that I can walk you through the entire solution. I'll just change some of the numbers, but I'll keep the essence the same as your question. Either email or Teams would be good for me. So it doesn't matter where you send it. Just quickly on Leslie's question, you have 6 over 9 plus x squared. You can have the integral is this would be an arctangent. So you go back to the formula sheet we have for arctangent. So here your a is equal to 3. So I guess if you mhm. Yes, go ahead. Okay, yeah. If not, I'll continue. So Leslie, for your problem, yeah, compare this with the arctangent formula. I guess the answer would be 6 over 3 arctangent of x squared. You're on evaluating arctangent, right? So the thing here is, what do you get? Have you gotten the integral already? So I can just walk you through with the arctangent. So what's your integral? So I guess you'll get 6 over 3 arctan of x over 3.
Yes.
So that's 2 arctan of x over 3. But you need to evaluate this from 0 to 3, right?
Yes.
Yeah, I'll do the first half, plug in 3, and hopefully you can do the other step, right? So I plug in 3, so I'll get 3 over 3 there. And this would be what? 2 arctangent of 1. Good? Now the thing here is how to evaluate arctangent of 1. So arctangent is asking you what is the angle whose tangent is equal to 1. But remember that arctan is restricted from negative pi over 2 to pi over 2, right? So sine, tangent, and cosecant are restricted in this interval, while cosine, cotangent, and secant is restricted from 0 to pi. So what does that mean is, okay, I'm looking for arctan of 1. So, and arctan is restricted on this side of the unit circle. So on this side of the unit circle, what is the angle that will give us tangent equal to 1? Do you remember? Yeah, Christina is correct. So the answer here would be pi over 4, because tangent of pi over 4 is equal to 1. So that means arctangent of 1 is equal to pi over 4. So 2 times pi over 4, that's going to be pi over 2. And then the other one is the other half, or what remains to be done to get the definite integral, is to plug in 0. So if you plug in 0, you get arctangent of 0. So again, the question is, what angle on this side of the unit circle will give us tangent equal to 0? Or when does tangent equal to 0? That will be equal to when the angle is equal to 0, right? So I guess the answer here is pi over 2. Okay, so basically it's going back to the pre-calculus concepts. So yeah, so if you still have some problems with that, you can meet with me during office hours. So if you want to have a walkthrough on this, okay. But yeah, if there are no other questions, then have a good weekend, everybody, and let's see each other again on Monday, hopefully with more of your questions. Yep, you're all welcome. Goodbye for now. See you Monday.